All right, is it 6:30 and I get to start then?
Yeah, you can start. Yeah, before that, um um for final presentations, for video presentations, if you access to the quiz question, then you can see the link to the presentation. So you can watch the video and see the presentation. And for video presentation, if you are submitting video presentation, make sure that your link is available to everyone. So actually one student has trouble to make it public. So just make sure that you log out everything, then still confirm that you can access to your video. Okay, so that's it. And okay, let's start. So today we have 5 presentation, and the first one is by the Jason.
Okay, I try to go through it quick. So hello everyone, my name is Jason, and today I'll be presenting my NBA season win analysis. Hope you enjoy. So I have an agenda, but I don't want to go through it time. So number one, my objective, I want to successfully predict NBA total wins per season by using their in-game statistics as well as their opponent in-game statistics. And by using like those statistics, each one could be a variable. And within that, I'm going to use stepwise regression to get a model. So my analysis plan, I kind of did my analysis on my own thought process because I played basketball for like 13 plus years. So I kind of just wanted to first regress only on offensive stats because that's something like I thought was important, but we'll see it's not really that important. And so then I only regressed on defensive and offensive stats, which kind of got closer to my model. I then used multivariable regression and chose the best model. And once I chose the model, I want to test the conditions to make sure it's a good model to use for like predictions and make sure it's stable. And if it all passes the model, then I actually will get to use it for predictions. So just a little background information on the data. I'm actually using data for the 2022-2023 NBA season because that's the most full season. I had 82 games played. The data itself, I know it's kind of blurry, but these are opponent stats. They have like a O, hence the O in front of the stats. And then these are the team stats. You'll see a T in front of it. And R is having trouble like importing the stats because their column name was like, it started off with like a number. So I had to make it start with T and O. So T, team stats, O, opponent stats. So my first step, because once again, I played basketball, I honestly just thought field goal percentage would be like a good way to go about it. Field goal percentage is basically just like, say you shot 3 shots and you made 2 of them, then you shot 2 for 3, so about 0.66%, or I'm sorry, 66%. So that's pretty much how field goal percentage works. So I thought it would be a good like indicator, which and it was like positive linear, but it only accounted for about 33% of variation, which is pretty low. So I noticed that field goal percentage wouldn't be just the only indicator I would need. So I then decided to split field goal percentage by 2-point shots and 3-point shots. If you see like in the bottom right corner, this guy named Steph Curry, he kind of changed the NBA game. He shoots a lot of threes, and like as the games go on, it kind of involves the use of the 3-point line. So when splitting them up, I thought I would see a bigger difference. But if you look, it's only about like a 0.31 and then 0.32 for 3-pointers. So it was kind of the same. And I decided, like, that's when I noticed, like, okay, it's not just about offense, like the saying defense wins championships. I'm like, okay, it really does. Like, data supports it. So that's pretty cool. So then I regressed to win to point differential. And what point differential is, it's kind of just like how much you either win or beat a team by. So say you won a game 110 to 103, then your point differential is +7, while your opposing team has a -7 point differential. And then like per the 82 game season, I just took the average of it. And so when I regress the wins onto it, we can see it's like a very strong positive linear relationship. And it actually had a multiple R squared value of 89.67%, which is pretty sufficient to me. But like once again, it shouldn't be a surprise as like basketball is not only about offense, but also defense. And point differential takes that into account because although you might score a lot, if you don't defend as well, then you're going to have a lower point differential. And as you can see, lower point differential equals less games won. So that's cool to see. So just a pool of variables that I had to choose from. I had 2-point field goal percentage, 3-point field goal percentage. I kind of split those up because that was my second initial idea and wanted to incorporate it into my final like project. Free throw percentage, assist, which you pass the ball, I mean someone shoots, steals, if you pluck the ball away or take it from the opposing team, turnovers, blocks, and total rebounds. There's offensive and defensive rebounds are components, but I just decided to put them together. And within that, each opponent's stats has like the same thing, just your opponents. And you can see here, I regressed it wins onto it in the coefficients. So then I did stepwise regression, and the best model I achieved had a lowest AIC value of about 81.82. It's R squared value. So I actually referred to the adjusted R squared value because multiple linear regression of 89%, which I thought was pretty sufficient for like doing projections. And some variables that left off for team steals. But when I thought about it, since turnovers right here are kind of the same as steals, turnovers also take into account like not like stealing the ball and like a human error on the team, just throwing the ball out of bounds. And which means they would pretty much be like collinear because the higher steals, the higher like opposing turnovers are. So that didn't surprise me it was left off. Opponent blocks were left off. I kind of thought because then field goal percentage, the team has higher blocks, then the overall field goal percentage would be lower, which made sense. And free throw percentage actually shocked me because I actually didn't take fouls into account. However, it took off free throw percentage. I really can't tell you why, but I thought it was just worth noting if people wanted to know. So then we checked model assumptions. My first check was collineary. I use variance inflation factors, which pretty much what those are. It's like it accesses the levels of multicollinearity, like regression analysis, because it can gauge how much predictor, like its variable's variance increases due to correlation with another variable. And how you can get these values, you can do like 1 over 1 minus R, like your R squared value, or you can just if you regress like if you wanted 3% percentage fifth values, just regress every variable onto that and take that R squared value. And anyway, if you have VIF values that are like pretty high, like 5 to 10, that can be a sign that they're collinear with one another. However, all my VIF values, as you can see, the highest is about 3.3, which like indicates no, like really low collinearity. So it passed that test. I then plotted the residuals over the fitted values, and it looked pretty good about the line. So I assumed it passed that visual test. And lastly, just the QQ plot, like you can see, it kind of like snakes about the line, but overall it seems straight. So I believe it passed all 3 tests for normality and no collinearity. So because it passed, I actually started using the model. I did this in Excel. So in this top huge thing, it's just like how I put it in Excel. So this is the 2021-2022 season. You have the teams, their actual wins, their predicted win from this Excel formula, and the difference, and then just the key. And it's just really a difference of 3, not more. I didn't mean to put that. But for the 2021 season, 2022, we got about 63% of teams within like 3 games of their actual, which I thought was pretty good. We had a mean value of 0.47 and like a standard deviation of 4.39. And our range was like only over predicting 9 and under predicting 8, which I didn't think was too bad. Our chart was pretty colorful, which is good to see. But then if we look to the right, the 2020-2021 season, I was kind of sad because I'm like, dang, the model sucks. But I actually realized that this is the COVID season. So there was 10 games shorter than what our actual like predicted wins took into account because COVID ended the NBA season early. So as you can see, like we have a higher mean with 3.664, but also we have like higher over prediction values because our model thinks they played more games than they actually did. So it actually tied in together. So then we forecasted the key change to just take that into account. We forecasted using 2020 to 2021 team stats and to guess 2021-2022 seasons. And we had a mean of about negative 0.86, which means on average, we underpredicted. But I mean, it's within 1 game of under prediction. So I was like, it's pretty good. We had a standard deviation of about 10.5 and possess a 95% confidence level of being within 1.96 standard deviations. But as you can see, we have like huge outlier values with negative 26, 14, 13, all those, negative 21. And so why like the huge variance? I actually looked into the season and saw we had pretty notable injuries with like Kawhi Leonard, Kevin Durant, LeBron James to go. And trades happen also. And so like that's why there's such a discrepancy between the predicted and the actual wins. Like if you look at these 4 gray ones, actually every player is listed either in a trade or an injury. outside the Grizzlies. So I thought that was something that could be an explanation to why the difference is so bigger than what it usually should be. And so conclusion, I had a takeaway overall, the model, when it came to predicting like the NBA season stats, given that season, it was pretty solid. It was pretty good. It was pretty good. A struggle point I thought was predicting NBA wins based off of prior season knowledge, only because you don't know like what's going to happen during that off season, like whether someone gets traded or you don't know during the season. Like if someone gets hurt, someone needs time off, someone's sick, you just don't know how many players are going to play on a daily basis. So that's a struggle point I can see the model having. Surprises to me were just the variables that I talked about briefly earlier, but then I thought about the whole turnover steal thing that kind of tied it all in. And some things I'd do different next time. I would like to account for injuries. I know like it's kind of hard to do because you don't know when someone's going to get hurt. But if you could maybe like take how many games they missed that prior season, you could probably fluctuate another variable. That could be a number. I don't know how that variable would like coincide with the model we already made. I don't know if it would change any other variables, but I would like to try to predict or at least account for someone getting hurt. So like Anthony Davis, for example, he usually gets hurt a lot. And if you can account for that in your model, I think it could be a little more accurate, but it would take a lot. And yeah, so the last thing, adding a variable that keeps track of the best two teams. Pretty much, yeah, it's kind of how I was saying, how I would just add a variable that monitors how many games they missed. And that is my presentation. Any questions? Sorry, if I can go back and if someone wants to see, I have trying to go through it quickly.
Sorry, I have one question before I ask a question. So you distinguish the teams by color, and that is the signifies its difference. I cannot really understand what that means. What the signifies are a difference of 0 or 1 or 2. What does that mean?
Sorry. So green means their actual wins that NBA season, and the wins we predict them to have.
Oh, okay. So that's the difference. Okay, I see.
I just had like a quick typo.
Okay, I see. That's fine.
Yeah.
I have a question.
Oh, go ahead. Yep.
For the win differential, that data point, where did that come from? Did that come from that season or from like a previous season?
Which one? I'm sorry.
Could you go back maybe a couple of slides? Maybe one more. Maybe forward a couple.
Like when like the scoring differential, or I'm sorry, which?
Yeah, I believe.
Was it the point differential?
Yeah, this
point differential. Yeah.
So you said like where did it come from? So within that chart, it's basically just like how, on average, pretty much how much you either outscore or lose by the teams. So like if a team was to on average always lose by 5, then their seasonal point differential would be like 5 or -5. But like a team always consistently won by like 8, this would be +8. And so I just thought it was a big thing because not only does point differential is take into how well a team can score, because you have to score to get points on the board, but it also like take into account how well a team can play defense. Like therefore their defensive stats would be like better, allowing like that true like scoring differential to like not just be an offensive statistic, but also like defense, if that makes sense. I used it's hard to see. I don't have it in here, but one of these charts, one of these like rows were differential just from the season. And so that's where I pulled it from.
Thank you.
Yeah, no problem.
Thank you. And sorry, one quick question. So you predicted the next year's performance with the prior year's performance.
For this NBA season?
The other way around?
I did, but I didn't predict using last year's data. I didn't predict this season, because we wouldn't no one would know in class. I wanted to actually present like if it worked or not. And since the season's only 20 games in, we wouldn't know until next April. So I used 2020 to predict the 2021 season. So I used that prior season.
So you go backward in terms of prediction. So you use 2022 data to predict 2021.
No, I use
No, the other way around.
the other way around. I use
Okay, great. Yeah, sure.
2022 data.
Okay, thank you. Okay, so that's meaningful. Yeah. Okay, so next presentation, maybe Vindhya, can you share the screen?
Yeah. Let's see. Can you see that?
Yes.
Okay. Yeah, so my project is on the factors that affect life expectancy in countries. And there are many factors that affect life expectancy, such as education, health coverage, genetics, and more. So it's just important to determine the factors that affect life expectancy, as well as the extent of their impact, in order to enhance the ones that increase life expectancy and sort of remedy the ones that decrease life expectancy. So we'll be focusing on 4 variables for each country. And these are variables that I was interested in regarding their impact on life expectancy. But also some of them, there wasn't much concrete information on their impact. So I thought this was a good opportunity to gain a little bit of insight. And these variables are the gross national income per capita, the criminality score, the literacy rate, and the type of government that each country is under. So the main objective here is to conduct an analysis to determine the effect of each variable on life expectancy, as well as any significant relationships that arise. And this analysis also includes determining any relationships between a combination of variables and life expectancy. Yeah, so there are 5 variables, and all of them are predictor variables except for life expectancy, which is obviously the response variable. And they are all continuous as well, except for government type, which is categorical. And it includes the categories of authoritarian. So that basically means that the countries are complete monarchies or dictatorships. And then we have a flawed democracy, which is where basic freedoms are granted, but we also have other issues. And that can be like less political participation and just trouble in overall government functions. Then we also have a hybrid regime, which is where there is really constant negative pressure placed on various government aspects. That could be corruption, harassment, and more. And then what happens is that it prevents a country from running a free democracy. So that's the main aspect there. And then you also have a full democracy, which is where full freedom and liberty are granted, and then the government essentially thrives on full democratic principles. And then on the right, we have the units for each of these variables. And then for the most part, the sample size is 195 countries, barring a few countries here or there during the analysis itself. And these are the data set sources, and these are the most recent data sets that I've acquired from these websites itself. Yeah, so to analyze the relationship between life expectancy and each variable, I use simple linear regression, scatter plots, residual plots, normal QQ plots for residuals, and Cook's distance. And I also did one-way ANOVA and the Kruskal-Wallis test for the government type variable. And to analyze the relationship between life expectancy and each variable after accounting for GNI, I used multiple linear regression, residual plots, normal QQ plots for residuals, and again, one-way ANOVA for government type and GNI. So this is a graph where the GNI is on the x-axis and the life expectancy is on the y-axis. And also, the bigger the size of the dot, the higher the criminality score for that country. And these countries are also grouped by their literacy rate percentages, with each group having a corresponding color, as stated by the legend down on the bottom right. And we can actually see here that Liechtenstein is an outlier country with a very high GNI, high life expectancy, and low criminality score and high literacy rate. And also Afghanistan, Somalia, and Mozambique are countries that are pretty low in all of those areas. So we can also see here that all of it is very crowded, especially between $0 and $50,000 in GNI. So, and when we look at GNI and life expectancy and regressing it, we can see here that there is no linear trend here whatsoever. And we can also see here that the residual plot is not random at all. And the QQ plot has some downward concavity as well. So we can say that there could be a relationship between GNI and life expectancy, but taking a log transformation of GNI possibly could allow for more linearity. And now we can see that it is less crowded. There is more of a positive trend here. And that same thing can also be seen when regressing it. There is more of a positive linear trend. And yeah, we can see that the multiple R squared and the adjusted R squared are both greater than the ones without the transformation. And the residual plot is much more random, and the QQ plot displays more normality. So we can say that there is a significant relationship between GNI and life expectancy. Yeah, so when looking at criminality score and life expectancy and then regressing it, there is a negative trend here. And we can see that as the criminality score increases, the life expectancy decreases by 1.37 years. And the residual plot is quite random, and you can see that the QQ plot is relatively straight, possibly. So we can say that a significant relationship does exist between the criminality score and life expectancy. And then we look at literacy rate and life expectancy, and then we regress it. And we can see that there is a positive trend, but a great bit of concentration nearing 100%. And this is also seen in the residual plot as well. But if you look at Cook's distance, it shows that most observations have similar contributions to the regression. Maybe barring a few observations, you have like the 34th observation and all of that. But we can also see that the QQ plot again displays normality, so we can say that a significant relationship exists between the literacy rate and life expectancy. And then lastly, looking at government type and life expectancy, we can see that in the box plot itself, the authoritarian has a wider range, but comprising the lower life expectancy years, while the full democracy comprises the higher life expectancy years. And then we can see that also in a flawed democracy and full democracy, the life expectancy is larger than the baseline of 70 years or 71 years in an authoritarian government type, which is that intercept over there. And all of them have small p-values. And in a hybrid regime itself, the life expectancy isn't that much larger, and it has a very large p-value. So we can say that the authoritarian and the hybrid regimes aren't significantly different, but the others are. And also when we look at the error and variance, and the assumptions itself are actually violated, and it just makes it really unreliable to use. So that's why we have to use the Kruskal-Wallis test, and it shows that the p-value is less than the significance level. And we can see that the residual plot shows a higher value for authoritarian and a lower value for full democracy. QQ plot is also relatively straight. So we can say that there is a significant relationship between government type and life expectancy. So the second part of my analysis is that we know that GNI is a significant factor in life expectancy. And we sort of want to see if the other three variables are significant in determining life expectancy after accounting for GNI, as well as possibly the extent of that significance. So when we're looking at GNI, the criminality score and life expectancy, and then we use multiple linear regression to do that, we can see that the p-value for GNI is less than the significance level, but the p-value for the criminality score is greater. And while both residual plots show randomness and the QQ plot shows relative straightness, when adding the criminality score to GNI itself, there seems to be no significance. So while GNI is a significant factor, there's no significance when adding criminality score, essentially. So we can actually accept the null hypothesis back here, and we can say we can say that. But when we're looking at GNI, literacy rate, and life expectancy, and using multiple linear regression for that as well, we can say that the p-value for GNI and literacy rate are both less than the significance level. Both residual plots display randomness, and the QQ plot shows to be relatively normal. So when adding literacy rate to GNI, which is already significant, we can say that that literacy rate is also significant, and that means we can reject this null hypothesis here. So, and lastly, when we're looking at GNI, the government type, and life expectancy, and using multiple linear regression for that, we can see here that the p-value for GNI is less than the significance level, but however, the p-value for the government type is greater, and the p-values for all the government types are also greater. So if you look at each one of them, and we can see that the hybrid regime could be marginally significant if we increase that significance level. And although we see here that the residual plots, the values are a bit higher and the QQ plot seems to be relatively straight, but nonetheless, there's no significance for the government type when adding that to GNI. So we can actually accept this null hypothesis right here. And then, yeah, so the major takeaway here is that all the variables by themselves are significant factors in life expectancy. But when factoring in GNI, the literacy rate was the only one that had a significant relationship. So that was sort of interesting there in that sense. So yeah, so that's it. Thank you.
Yeah, thank you. So it's very clear presentation. So does anyone have questions?
I have a question. How is criminality measured? Is it like each country measures their own criminality based on their laws, or is it more of like an objective set of like criteria that each country is measured by, like the same rules?
Yeah, so criminality score, I think here, so it says here, so it's a score that ranges from 1 to 10. So it's actually, so when we look at, so this is like, this data source here is an OCI index. So what they did was, they just, I guess they just used their own, they use their own data. So various criminal aspects, I guess, maybe if they did something illegal or something, they just took a bunch of different things that they felt was criminal, and not sort of on an opinion base, it was more on a fact base, and they just created a score from 1 to 10 and just deemed each country as that number. So
Thank you.
Is that an organization made by United Nations or?
it is a government organization. I can't remember which one it was, but if I click on the link, it would say that.
Sure.
Yeah,
that's fine. Yeah.
Okay. Do you want me to click on the link or?
That's fine. Yeah, I
Okay.
just wonder. Yeah.
Okay.
Yeah.
Let's see.
Yeah, generally speaking, United Nations, OECD, those World Bank, IMF, those are put significant, efforts to get data in the same criterion. So yeah.
So it is the Global Organized Crime Index. So it's so it's like an index, and then you can see here it's like they have different things about criminal whatever for each country. So
yeah. So does anyone have more questions? Yeah. Yeah, so basically the result indicates that if you inherit $10 million, then you don't study at all. You are doing fine. Is that right?
That could be. That could
yeah,
be.
maybe, the statistics may be different, within country, but yeah, maybe overall implication is that. Great. So yeah, so it's good. So if you're making presentation on next week, so you don't really have to stick with including too many variables. So this course is statistics course. So the clear interpretation of statistical models is more essential than the forecasting results. So yeah, it's a good model. Okay, so next one we have. Alexander is here. Okay. Can you share the screen?
Yep.
Yeah, you can start.
Good evening, everyone. I think it was just mentioned at the presentation before that I wanted to see if defense actually does win championships. So just a quick introduction about my project that I'll be investigating that if having the best NBA defensive statistics determines if you have a better chance of winning an NBA championship. We'll be looking at several different categorical and continuous variables from the 2022-23 NBA regular season to determine our outcome. We'll be basing our data around 3 different NBA teams: the Denver Nuggets, who won the NBA, who are NBA champs from last season, had 18 players; the Atlanta Hawks, who finished 15th out of 30th on NBA records with 20 players; and the Detroit Pistons, who had the worst NBA record with 22 players. The data. So our 3 categorical variables will be age, NBA team, and NBA position. Our 9 continuous variables. I wanted to note before that we begin that all continuous variables will be based on per 100 possessions, because we want to exclude any anomalies the data might show. For example, if a player played a limited number of games, or if there was injuries that could have limited their season. So our 9 continuous variables are defensive rebounds, defensive rebound percentage, which is the amount of available defensive rebounds a player grabs; steals, steal percentage, the percentage of the team's total steals; blocks percentage of the team's total blocks; defensive rating, a player's efficiency in preventing the other team from scoring; defensive win shares, the number of wins contributed by the player due to defense; and defensive box plus minus, the number of defensive points a player contributes above the league average, which is 0.0. And these two links are where I grabbed all my data from. So training the data. So the original data had about 679 rows with all players and all teams. And then I had to trim the data to include just the 3 teams: the Nuggets, the Hawks, and the Pistons. And we got 60 rows. So an overview of the data, I wanted to see if the position, the roster breakdown by position made a big difference on 3 teams. And as you can see, the Pistons and the Hawks have the relatively same roster breakdown, versus the Nuggets have a lot more power forwards and centers on the team. And then I also wanted to see the player ages by team to see if that really made a huge difference. And the Pistons have a slightly younger team with a mean of 24.27, with the Nuggets having a little bit older of a team with average age being 26.72. And then I wanted to see all players' defensive ratings to see what the average would be. So the mean average was about 115.5. And I was curious to see how many teams were below the first quartile. And I was surprised to see the Nuggets, the NBA champions, had 7 players below the first quartile. And our one outlier is from the Detroit Pistons, Stanley Umude, with a defensive rating of 44. And then I wanted to see if there was a relationship between defensive rating and defensive box plus minus, which a lot of the players are in the top left quadrant, which is they have a high defensive rating but a lower defensive box plus minus. And then I wanted to start with our model with a simple linear regression model to investigate the relationship between if having better defensive statistics will improve the team's chances on winning an NBA championship. Defensive box plus minus will be our dependent variable or y variable. Each defensive statistic will be our independent variable. And then we'll have our error return, and then our equation will look similar to that. We would also construct a fitted line curve over each scatter plot, and then we would repeat for each team we had listed. And then for our null hypothesis is that every team will have the same defensive statistics, represented by the equation mu1 is equal to mu2 equals to mu3. And we will set our significance level at 0.05 to reject the null hypothesis. If we fail to reject the null hypothesis, we will formulate an alternate hypothesis that all 3 NBA teams have different NBA defensive statistics, and represented by the equation mu1 is not equal to mu2 is not equal to mu3. And then as you can see for the Denver Nuggets simple linear regression, that the QQ plot follows a linear line. And then our residual plot is slightly random with a lot of points in the top left quadrant. And then for the Atlanta Hawks, you can see that the Hawks also have a linear linear model for their QQ plot, but not as tall as the Denver Nuggets was. And as you can see, that most of their points are in the top right quadrant for the residual plot. For the Detroit Pistons, they have a lot smaller linear regression line versus the other two teams, the Hawks and the Nuggets. And you can see on the residual plot that a lot of their points are in the bottom left quadrant, which is not the best. And then I wanted to do an ANOVA model, a one-way ANOVA model to test the difference between defensive statistics between each team. So we will investigate the relationship based on each defensive statistic mentioned previously. And then our equation will be yij equals to alpha I plus our error term ij, with ij using the jth player on the I team, the Nuggets, Hawks, and Pistons. Our null hypothesis will stay the same, that alpha 1 is equal to alpha 2 is equal to alpha 3. And then alternate hypothesis that each team has different statistics. Alpha 1 is not equal to alpha 2 is not equal to alpha 3. And then I wanted to note that steals percentage has been omitted for the ANOVA analysis, as it's very similar to the steals per 100 possessions data point, which causes the data to be slightly corrupted. So as you can see, for our defensive rebounding and defensive rebound percentage, that our p-value is a lot bigger than our significance value 0.05, and the f value is slightly higher, meaning that they all had similar data. So for steals and defensive rating, our p-value is still slightly above our significance value of 0.05, with the f value of steals being 1.002 and defensive rating being 0.175. For the steals, they have slightly different data, versus defensive rating having very similar. For blocks and blocks percentage, our p-value is around 0.58. For blocks, the p-value is 0.587, and for the blocks percentage, the p-value is 0.571. With the f value, f statistic being around 0.537 for the blocks and 0.565 for the blocks percentage, meaning that they both have relatively the same data for each team. So then for defensive box plus minus, our p-value is 0.546, which is slightly above our significant level of 0.05, as well as our f value being 0.611, which means that they all have very similar data points. And then for the defensive one shares, our p-value is 0.0284, which is below our significance level of 0.05, with our f value being 3.793, meaning that they all have a lot of different data points. And then, so far, our ANOVA takeaways is our f statistic remain relatively low for most defensive statistics, meaning that there's not too much significant difference between each team. Our only defensive one shares is below our significance level of 0.05. We reject our null hypothesis only for defensive one shares, and others remains relatively high, around 0.4 to 0.6. And then we want to use two keys method to consider the differences of means for each pair. So as you can see through all the for most defensive statistics, our adjusted p-value is still a lot higher than our significance level of 0.05. And then as you can see for defensive one shares, for the Detroit Pistons and the Denver Nuggets, our adjusted p-value is below our 0.05 significance level. So so there's some so our takeaways is that the adjusted p-value between Detroit Pistons and Denver Nuggets is below the significance level of 0.05 for defensive one shares. Then all other adjusted p-values are relatively high, most above 0.5. So in conclusion, there is a relationship between winning an NBA championship and defensive one shares. The defensive statistic among NBA teams are razor thin for the most part. Nothing other than defensive one shares plays a significant role in winning an NBA championship. And then, given more time, I would like to extrapolate this data over the past 10 years to see if the data and results remain consistent. And then, overall, we reject our null hypothesis that all teams will have the same defensive statistics based around defensive one shares. Thank you, everybody.
Yeah. Thank you. Does anyone have questions to Alexander?
I have a question.
Yeah.
Who's that one outlier?
For which one?
The one for defense. The
Yeah.
guy was like Stanley.
The box spot.
Yeah, I
For
think
this
so.
one
Yeah.
right here, down here.
Yeah, Stanley.
Yeah, Stanley Umude.
Who is he? Why does he have such a?
So I did a little bit. So I'm a fan of the Pistons. So I've watched a lot of their games this year and last year, and he was brought on to at the end of the season while they were tanking to lose most of their games. So he was not the best player. That's just from the eye level, and the stats back it up.
That's interesting. Thank you.
Yeah.
Does anyone have more questions? Yeah. Yeah, so this is also interesting analysis as well. So the JSON uses teams as the sample units, and Alexandar uses the players as sample units. So we have different aspects of the analysis. Okay. And the next presentation, Ryan is here.
Yep. Can you hear me okay?
Yes.
Give me
Can you
one
share the
second.
screen? Yep.
Yep. Okay, that looks like the right screen. Okay.
Yep.
Brief disclaimer. If I do drop out to my Wi-Fi, I'll probably be back in 15 seconds. It has been doing that all day. All right. So my presentation today is about low access food areas in Michigan. So a little bit of important terminology before we go ahead. So when we're saying low food access, we're talking about places with very limited access to affordable, nutritious foods. And these are typically found at supercenters, supermarkets, and other large grocery stores, which these three specifically make up for about 84% of SNAP redemptions. So think any government assistance like food stamps, the majority of those redemptions are happening at these places. And we'll also be talking about a lot about census tracts today. These are just areas used in the census that are like small, relatively permanent subdivisions of a county, each of which has a unique numeric code, and they're supposed to average about 4,000 inhabitants per tract. If the population rises above 8,000, they kind of just cut it in half to try and keep the average about reasonable. And here's a bit of an example of these census tracts. So as you can see, because of the tract's relation to density, you can kind of tell there's a lot more denser areas towards like the Detroit area or other like major cities. And that will also become important as we're talking a lot about urban and rural areas in this presentation. So our goal for today is to design a model that can predict the likelihood of an area being deemed low access so we can analyze the factors that make an area more at risk. We're going to do this in three different ways. We're going to define and classify variables we deem possibly important to our model, determine the correlation of these variables for a better idea how they'll all relate to each other, and we'll use logistic regression to create a model designed to predict the likelihood of an area being deemed low access. And very brief disclaimer also, because of the sheer scale of, being low access and the variables that go into it, I'm not going to be able to sit here and pretend that it's going to be 100% accurate. But the idea is to find predictors that are correlated and to be able to use those that we can find to be able to do some sort of analysis with that. With that, the data I chose came from the U.S. Department of Agriculture's Economic Research Service. Long story short, after the 2008 Farm Bill was passed through, they were requested to look into the extent of food deserts, which have now been renamed to low access and low income areas to be more accurate to what they represent statistically. And as you can see below, there's sort of a map here of these low access areas we're going to be talking about with our definition that I'll go into a bit more later. But as you can see, it's a very widespread issue across the entire U.S. And all the data, including an interactive map of the U.S., is given with the link here. As far as the actual data goes, there's a lot going on here. There's about 147 different variables. But a lot of these are binary flags that have been used as predictors that have been predicted by other variables in the thing, or they're different subsets or general uses of similar ideas. But either way, it's too many variables. We're going to have to limit our scope later on. And speaking of limiting our scope, the data set does include about 72,000 observations, which is a lot. And also when you consider the difference in US between geography and weather and all that. And as you can see from before, the various spread between each state is very different, obviously, between the low access food areas. So we're going to limit our data to only consider census tracts in Michigan, which still has a bit under 3,000 observations. So it'll be easier to work with, but it should still be pretty applicable. As far as the variables to be considered, we had a lot to choose from, but I chose specifically 9 to consider. So we have the total population. All these are in correlation of the census tract that's being worked with. So total population of the tract, proportion of white population, median family income, poverty rate, the urban rural flag, which is basically a binary value that's just it is a 1 if it is considered urban, 0 if it's considered rural. And then proportion of population under 18, proportion of elderly population, which would be over 65, the low income population in that area, as well as the number of housing units in that tract. And a brief clarification of a few variables here. We're going to be using the predicted variable as the low access flag to predict to. The one we're using from the data set determines that a person is in a low access food area if the person in that area, in an urban area, averages further than 1 mile from the stores previously mentioned, or 10 miles for those that live in a rural area. So the criteria sort of changes depending on whether you're rural or urban, which makes sense to do. Because they do this, I did want to leave the urban rural flag in as a predictor to sort of see if there was any amount of like difference between whether or not we might want to consider changing that definition or use a different one. It's also very likely that between median family income, poverty rate, and the low income population, one or multiple of these will not be statistically significant because they all 3 measure something so closely related. But since we're looking for the best approximation, we're going to include all of them and get rid of them all later if they're not relevant. As far as what the actual variables look like, as you can see here with the density I talked about earlier, the majority of them are going to be urban, with about 3/4 of them being urban. And with our definition of low access tracts, about 1/3 of the tracts were considered to be low access, about 2/3 were not. And then the histogram of the total population, as you can see here, they do hover around 4,000, maybe a little bit less, which made sense with our definition of the census tracts. And the proportion of white inhabitants, you sort of see the uptick at the very end here and sort of towards the end, but the majority of the tracts in Michigan were predominantly white. And then really quickly, median family income hovers around 70,000, which is about expected. Poverty rate below 20% for the vast majority of the census tracts. I was a bit surprised at the proportion of under 18 inhabitants being about 25%. But when you look at the elderly proportion, which is about 15%, and you combine those together, which is about 40, and those are being the very extremes of the age range, it kind of makes sense that the rest of the 60% falls in between 18 and 65 sort of thing. And then we have the correlation of the data. So as you can see, there's not a lot of variables that very closely correlate to each other between all together. There are a few that I feel are important mentioning. You see poverty and what proportion of white inhabitants, as well as poverty and like median family income, obviously are going to be inversely related. The higher the median family income is, the less likely that there's a lot of people in poverty in that area. And then also we have the elderly under 18, under 18 category, which I wasn't super surprised. There was an inverse correlation, but I was surprised it was that strong as it was. And as you can see here, the main ones we're going to be looking at are the low access flag and the correlation with the other variables, which was interesting to me because I also saw that the most closely correlated was the urban rural flag, which, like I said from earlier, we were kind of hoping with our definition, taking that into account, that wouldn't be as major of a factor. But we'll go into that a little bit more as well. But long story short, because these are not very specifically correlated does not mean they're not statistically significant, but it's also just likely there's not just one or few variables that are going to dominate the others. It's kind of just all like a big mixing pot, which you sort of expect in this like real world example. And then we will be using logistic regression. So I know we talked about it in class, but just to really briefly run it back. We are going to predict some binary variable y such that all the predictors multiplied by some coefficient will be able to predict y. but doesn't really make sense because y can only be 0 or 1. So we need to use a linker function. So in this case, we'll consider pi to be the expected value of y. So then we can just do that instead of y in the equation. So now f can give us a value between 0 and 1, which is a lot easier to work with. And so for our purposes, we'll be using the logistic model. So f of pi is going to be less than similar to log pi over 1 minus pi. And when you look at the actual logistic regression here, I was kind of surprised to see that so many variables were considered statistically significant. The only ones that were major issues in my eyes were median income and poverty rate, which again made sense because since low income is so statistically significant, it does kind of make sense that all three of them are not going to be all necessary when considering the model. And so I played around with it a little bit. The main one I did remove was poverty because poverty rate was because it did seem the least statistically significant. And when I removed it, it dropped a whole 1 point in the AIC. So clearly something must be going well. It's probably mostly, it probably doesn't mean it predicts that much better. It probably just means that because it dropped a variable, AIC wants the least amount of variables in the model. So that's probably the most likely cause. But as you can see here, median income is still not particularly significant. But when I removed it, the model got upset and jumped a whole 60 points. So leaving it in there does make for a better model, apparently, which my belief for that was probably because there are so many other factors going into it that the code just kind of assumes that because this is predicting it, that's the reason why. But it could be because of a lot of other different things. So this was the model after I removed a lot more variables in this, but long story short, after removing all of them, we still are left with this one, which has the lowest AIC and seems to predict the models the best. And then I pulled out the coefficients of all the variables here, along with the averages of all these. So as you can see, just because the coefficients are really small does not necessarily mean they're insignificant. Because as you can see with like total population, even though the coefficient is only 6.9 times 10 to the negative fourth, the average predictor value is about 3,500. So obviously that's going to still be a pretty predominant factor. So you can sort of see here that is in the two different categories, in the positive and negative. So you can sort of see, depending on whether you're looking to actually predict whether it is or look at what factors it probably won't be low access in, you can do that. And then I did find a few coefficients kind of surprising. I found it surprising that proportion under 18 was so high, especially considering the other proportions were not that much higher, as well as median family income and low income population both being negative, meaning that it was like less likely to be low access, was kind of surprising. But I have a theory with that we'll talk about in a second as well. So as you can see here, these are just some of the more problematic graphs that I made out here. So as you can sort of see, low access flag, one being they are considered low access, the bottom one being they're not considered low access. You can sort of see in like proportion of white inhabitants, there's sort of some bias. If an area is low access, then it's predominantly white for the most part, or it's likely to be. Median family income, it kind of looked about the same density wise, but there were a few outliers here where the median family income was like incredibly high, but it was still considered low access. It's kind of my belief that has something to do with our urban rural definition that we were talking about earlier. As you can see here, for low income, you can kind of see that there is sort of some density, like the density really does seem to pick up. I really should have added some jitter into this graph so it's easier to tell, but you can sort of still tell the same general idea. And the proportional under 18, you can kind of tell it's still about the same density wise, but there does appear to be some like very slight amount of more of higher density, just like in the low access flag. So my guess is that's probably why that's happening. But because of these coefficients, and especially because of these these median income things, it's kind of my belief that there's a lot more obviously you can look into with this. Obviously a lot more a lot more variables can be added for a more accurate prediction model. I think there's so much more that you can do. I listed a few of them here, but I also think an in-depth look at specific tracks over a period of time can give more insight into the correlation between these variables specifically, just so we can see how they might be changing over time with other. As well as you can see by the previous plots, I believe there's a pretty high likelihood that our definition of low access for rural areas might have a fairly substantial effect on our data. As you know, especially if a very high median family income area is considered low access, it's very likely that they just own like a lot of land around the area. So it's very possible that that's also a factor, just because simply if it's considered rural, even though a lot of people that live in rural areas can still have a lot of money. So there's probably some definition we can change there, whether it be with the distance or adding more criteria specifically. And again, kind of like I said at the beginning, I would not say this data is conclusive enough to fully definitively predict the model 100% accuracy. So I think there's a lot of other things that go into it, and there's a lot of more stuff that we could do with future data. Thank you. Do you guys have any questions for me?
I have a question.
Yeah.
I was just curious. You said you had 147 variables initially. I was just curious what some of the other ones are, if you have them on the top of your head.
Yes. So a lot of them were other binary values. Like as you can see here, the ones on the right were all different low income and low access tracts. So there were about like 20 of those that I didn't want to use as predictive variables. And then there were quite a few also based on there were multiple different race types and then multiple different ways of categorizing race. So there's probably about another like 20 or 30 of those. I just wanted to simplify it. I felt like it was kind of all more encapsulating to just do one. But yeah, like I said, the majority of them were not explicitly their own data point, but they're kind of derived from others or just sort of more general than other data points.
Gotcha. Thank you.
Mm-hmm.
Does anyone have questions?
Actually, I have a question.
Mm-hmm.
I think maybe I don't think this is present in the data you have, but do you think that would be any difference between like the Lower Peninsula and the Upper Peninsula?
I think there definitely could be, especially considering that there's so much more like urban areas that are like even just like spread out in the lower half. Because especially in the upper half, you still have dense areas, but it's kind of more sporadic. I definitely feel like there could be, and especially if we didn't live in Michigan, it might be better to have a more contiguous state to work with. But I felt it was more applicable for us since we're here to do Michigan. But I do agree, there probably is some level of difference there.
Thank you.
Mm-hmm.
Yeah, so I have some statistical comments. So the logistic regression that you make kind of a scatter plot, and of course the observations are overlapped each other because we only have two possible values. So if you want to avoid that, then you can use the jitter plot, the JITTER jitter plot.
Mm-hmm.
Then you can add random noise to the response value, for example, 0, 1. So when you make the graph of x and y, you can type the plot x comma jitter of y, then you can make some artificial noise to avoid some overlaps. So yeah, that can be a good way. And yeah, but anyway, so logistic regression, our class only covers very minimum materials. So yeah, you can study more later if you take applied regression class. Yeah, and also you can do the ANOVA analysis to decompose the percentage of variation explained by each variable. So that may be also interesting topic. Yeah. But overall, it's very interesting because you just keep the meaningful variables, so we can see the meaning of each variable. Yeah, that's great. Okay, so any other questions? Yeah, it's very interesting data, and the introduction is very informative with good graphs. So yeah, I like that. Okay, so the last one, Sonali. Yeah, and if you have questions to Sonali, you can put in a chat. Okay, so then she can answer later after her presentation. Okay, you can share the screen. Yeah, you can start at any time.
Okay. So I studied the excessive use of force by police officers and the characteristics of those involved. So this is my data. So introduction, there has been considerable discourse and public interest on the conduct and behavior of police officers in recent years, and many cases of unfair conduct and assault by police officers have been reported in the news, particularly the bias of police officers against certain minorities of special interest. So in this analysis, I wanted to analyze the characteristics of the officers and such subjects in cases where the officers used excessive force to handle situations, and see if we can find any characteristics that result in more cases of excessive force. So the data set that I found was the New Orleans police data gathered from 2016 to 2023 of 3,570 different incidents. It's data from 2016 until the current day that's updated every day. And it contains 33 different variables with information about characteristics of the officer, including the age, height, and weight of the officer, environment such as what the weather conditions were like, and how bright or sunny it was, and also characteristic data of the subject, such as the age and height and build and other things that we're gonna be looking at in this analysis. And so we're interested in determining the difference between cases where excessive force was used versus cases where the subject was not injured. Because this is basically a data set of situations where the police officers did use force when they were dealing with the subject, and I just wanted to see if there any characteristics of the police officers or the subject that determine whether they use excess force and actually injure the subjects. And there was a lot of data cleanup that had to be done because the data set contained multiple it included all of the instances, even instances where there are multiple subjects and multiple officers involved in the altercation. And I just, for ease of analysis, I took out all of the in situations where there were multiple subjects involved, and also I I kept in the incidents where there were multiple officers involved. And then I ended up with 11 variables. So the response variable is a binary variable. So similar to the presentation before me, I'll be doing logistic regression on my presentation. And the predicted variables, they range from the use of force, the reason for the use of force, to the service type, the race of the subject, build, gender, age, race, and the race of the officer, whether the officer was injured or not, the gender of the officer, and also the number of officers that were involved in the altercation. So I did not, I don't have the number of subjects because I took out all of the instances where there were multiple subjects. But there are still multiple officers in the data that I collected for some of them. So the objective is to determine how each of the predictor variables influence the response variable by observing plots of injured versus non-injured subjects for each categorical variable. And so I forgot to mention most of my data is categorical, and I have two continuous predictor variables, which include the number of officers and the age of the subject. And so I'll be performing logistic regression analysis on each predictor by using the equation f of y equals beta naught plus beta 1 x1 plus beta 2 x2, and I'll be applying logistic regression line graphs of incidence of injury versus fitted curves of each continuous variable to analyze the continuous variables. So here are now I'll just go through all the characteristic the categorical variables. So the subject race, it does seem to be like, so I have the subject race, and then I have a plot of how the subject race by like proportion of the subjects that were injured and proportion of subjects that were not injured. So it seems like Black is the race that seems to be appearing with like the most frequency, and also whites. And it doesn't seem like there's much differences between the injured versus uninjured subjects, but we'll do a test on that later to see if there is a significance of race on the injury rate. And same for build, there doesn't seem to be much of a difference. Gender of the subject, there does seem to be slight differences. Like there are no cases in when the subject is injured where the gender of the subject is unknown. So I thought that was interesting. And then looking at the officer race, you can see there are several differences between the injury and the injured subject versus the uninjured subject graph. And when you look at service type, you can see that there's also quite a few differences between the graph of the injured subject and the graph of the uninjured subject. So it seems like there seems to be a higher correlation of subjects that get injured in traffic stops, and when the police officer is arresting the subject versus in the uninjured graph. And then with officer, when in situations where the officer is injured, there doesn't seem to be much of a difference. So, and then lastly, there's the reason that use of force, which the reason that the officer used force in the altercation. So I used a logistic regression model. I wanted to just test each since a lot of my variables are categorical, I wanted to be able to just test each individual data point or each individual variable against the response variable. But since I'm dealing with the variables that could influence each other, I decided to conduct tests and find out which variable like seems to have the most influence on the incident of injury. So I found that the use of force, the reason for the use of force, seemed to have like a really significant p-value. And so that is the and also the service type. So I decided to test both the use of force and the service type against each other. Like, so the null hypothesis in this situation is that the use of force, the reason for the use of force is the only variable that impacts incident of injury. And my alternative hypothesis is that the service type and the use of force, the reason for the use of force both impact the incident of injury. And looking at the factors of interest, so after doing a logistic regression analysis on this, I found that there were both the use of force and the service type had several factors that were accounted for in the analysis. And so I just pinpointed the ones that had significant p-values. So all of the factors that are listed over here are just the factors that seem to have a significance on the incident of injury. So for example, we have refusing verbal commands is a factor that seemed to have a pretty significant, not a very big effect on the incident of injury, but the one that's really stands out here is when there's a weapon exhibited. That one has a really significant p-value, which tells us that this is a variable that really influences the incident of injury for the suspect. And one second, I just want to turn off. Oh. Okay. So, and it seems that use of force has a lot more factors that seem to influence the incident of injury compared to the service type, which only has 2 factors. And then I also did a ANOVA test of deviance with the service type and the use of force, the reason for the use of force. And I found that the deviance of service type minus the deviance of the use of force is only 17.751, while the deviance for the use of force, the reason for the use of force is a lot higher at 115.367. So moving forward, I decided to also test the service type as the null hypothesis. So the service type influences the incident of injury. The service type is the only thing that influences the incident of injury, and the alternative hypothesis that the service type and the reason for use of force both influence the incident of injury. And from here, I found similar results for, like, at least for the factors. These were all the same factors that came up, and these were all the same factors that had like significant p-values. But I did find that the deviance for service type was higher in this situation. But the reason for the use of force, the deviance of that variable was still a lot higher than the deviance of the service type, which means that it impacted, or it influences the injury incidents a lot more than service type. So that's why for all of the following variables, for all the rest of the variables, I decided to use a linear model with the reason for the use of force as x1, and I decided to use a multiple logistic regression model to test all of these against the reason for the use of force.
12 minutes.
Okay. So so as you can see here, like I have all the variables listed here. The ones with significant p-values, the significant factor p-values include the number of officers, the officer race, the whether the officer was injured, and the service type. And I did a ANOVA test of the deviance, and I found like that in particular whether the officer was injured or not had a much bigger deviance than the rest of the factors, and the p-value of the deviance it seemed to be much higher for the number of officers, the subject race, and whether the officer was injured or not, which leads us to reject the null hypothesis for 5 of the variables, and to fail to reject the 3 of them. And then I also have a logistic regression line graph of the continuous variables. So our continuous variables were the subject age versus whether the subject was injured or not. And you can see here that it seems like the age age range from 20 to 40 seems to have a really high proportion of subjects that were not injured. And it seems that when the greater the age of the subject, the more they seem to get injured. And you can see that with the faded line that I did in the next slide. It's not a very like prominent line, but it does, like, when you zoom in on it, you can see that as the subject gets older, they have a higher proportion, the percentage of getting injured is higher. And so but it's not also, I'm not sure exactly how reliable this is, since there are some outliers, especially in the beginning, that in the first graph that show how that show that the subject gets injured more. And then I
Wrap
did
up
the same
presentation. Sorry.
Okay, I did the same for the number of officers and found a much higher rate of land. And then in conclusion, the race does seem to play a significant factor in whether officers use excessive force, and other factors involve the reason for use of force, the number of officers, the officer's race, whether the officer got injured or not, the age of the subject, and the service type. And that's it.
Thank you, Sonali. So does anyone have questions? If you type as well, then it may help for.
I have a question.
Yeah.
So I heard that like judges, when they get hungry, they sometimes serve higher sentences. Is it possible that cops could also like be harsher if they're hungrier as well?
I think that could definitely play a factor into it. I think this data was only taken, like it's basically like the police officers record this right after they meet the subject. So if like the like meeting the subject like at a traffic stop or whatever, like this is just like the immediate data that the police officers say off the top of their head. But yeah, I definitely do think it would have been interesting to see like whether the judges impacted or not.
Thank you.
Interesting point. Yeah, it can be significant here. Just one comment on the plot. So we haven't discussed the residual plots for logistic regression. So in logistic regression, the y values are always either 0 or 1. So possible error value is only 2 given the data point. So yeah, so but the applied regression analysis course will discuss more details about the diagnosis of logistic regression. We haven't discussed it. Yeah. Okay, thank you, Sonali. And I think that these are all presentations. So hopefully I will upload the 2 or 3 presentations, the video presentations, and you can make comments. So comment form for today's Zoom presentations are already available in Canvas. And also the student evaluation of teaching. So that is due tomorrow. So I hope that you can submit it. Yeah, I think the 30% of students submitted, but especially online courses, it's important to ask you to submit because the submission rate is always low. Yep. Do you have to make comments on your presentation? Who's my presentation? Oh,
I didn't mean like your own presentation.
Yourself, you mean? Yeah. Yeah. You can make you can put this is my presentation or something. So then I will give you 1 point.
Okay. When we make comments, like, do we have to like score the presentations, or is it kind of just...
always you will get 1 point as long as you wrote meaningful things. So if you type just NA or something, you will not get points. But as long as you comment on it for 15 words or more, that you will get full credits.
I just mean, because I know you said like the grading of the presentations will be based off like the class comments. Do we have to like leave a score or something, or do we just
no, the comments do not affect scores. So the only factors affecting your presentation is the quality and my evaluation, and also the vote by students. So I will ask you to vote the best 3 presentations at the end of the semester. So that will give you some
Thank you.
bonus credits. Yeah. Okay, so do you have any questions? And the next week we have more presentations. I think that we have 1, 2, 3, 4, 5, 6. I think 6 presentations. So just to make you available until maybe like 8:15. That is yeah, a little longer class.